really good shape. Oh my God.
Okay? Aviation weather. Now, I got to tell you, I don't see a whole lot of coffee out there on these desks, and that might be a problem. Aviation weather. Now, I try my best to make this kind of exciting, and I enjoy aviation weather. I really, really do. But it's a dry subject. It's something that's sometimes what pilots would consider boring until they get faced with that one situation where, oh my gosh, I wish I knew better about weather now, okay? So it's one of the biggest hazards that you'll face as an aviator, especially as a general aviation aviator, because really nobody's shooting at us, okay? Well, Tamiami Airport, they're actually shooting at the airplanes as they went by. Well, that's Miami. And that only lasted for a couple of weeks. But, all right, not likely. Nobody's going to shoot at you. Your biggest threat out there is indeed the weather, okay? How many thunderstorms do we get here in Moscow every year? Okay, for those of you that are going to Florida, I want you to spend some time in your life, okay, studying a little bit and looking at severe weather in South Florida because it becomes rapidly dangerous. There's a lot of energy down there, and if you're in the airplane and trying to make things right with your maker, it might be because of a thunderstorm. These things are pretty severe. Does that mean that there's a likelihood that I'm not going to be able to fly in 1, 2, 3 days, a week, whatever? No, probably not. The good thing about it is it rapidly changes, so it'll come, it'll go. But you don't need to be where that storm cell is or where that activity is when it's occurring. Okay, it'll damage, break the airplane. All right, so anyhow, a little bit of motivator on that. Let's get into weather. The Guided Flight Discovery, Chapter 6, for those of you that are following along in Jepson. Pilot Handbook of Aeronautical Knowledge, Chapter 12. Remember our advisory circulars. These are a real thing. You've got a great, great advisory circular. It was revised in 2018. Previously, the most recent edition was 1974. So Advisory Circular 00-6B is recently released. They just added color to the pages and applied just a little bit of work around on it, but it's very, very good read, okay? It's kind of long, but it has some more in-depth information once we get going. Section A is all basic weather theory. If you know anything or you've taken any kind of class before about theory, it is just that. It's theoretical. I'm not going to describe situations that will always occur or look for this, and that's exactly what you get. What I will do is give you some characteristics of. Look outside, you see these type of characteristics. Look on your chart, you see this type of phenomena occurring. Here are here's the theory behind that. Here's the idea of why that weather is forming and what could occur as a result of that weather. All right, key terms. Got to have some key terms. Atmosphere, troposphere, tropopause. Pretty much everything that we deal with as far as weather is below 36,000 feet. Okay. Remember Howard Hughes tried to get that constellation up above the clouds and for a nicer ride. That is a much nicer ride up there. Everything that we deal with is, for the most part, below 36,000 feet. And that's where the tropopause exists. Stratosphere is above that. My jet pilots, as soon as you guys get those jets and start throttling up, you're going to go straight to the stratosphere. Good times up there. Mesosphere, unless you're taking a rocket, you probably won't get to that, or the thermosphere. So, I don't know, we've got some astronauts perhaps, but without a rocket, you probably aren't getting up there. Some things that we need to address: circulation, convection. This is what forms our weather, what makes the weather, and it describes exactly the power of the weather that we have down there in Florida. Isobars, pressure gradient, high pressure, low pressure, ridge, trough, and cowl. Each one of those describe where do I have different pressures on the atmosphere. How does the weather flow into a new region? And what kind of shakeup occurs as a result of that new weather flowing into the region? Pressure gradient force, which is going to describe how fast the wind moves. And then Coriolis force will describe which direction does it move exactly. Coriolis force is kind of fun. Hopefully we can cruise through that one. It is a really nice idea, but you got to take the perspective that you're a little uncomfortable with. So we'll take that ride together. Frictional force, all the air that moves and the wind that moves around us is affected by buildings, by cars, by trees, by everything about 2,000 feet and below. That's your frictional force. Sea breeze and land breeze are just local weather patterns. Same type of idea behind circulation and how much heavy air or cold air, hot air, how much of these things weigh and what causes circulation. Just on a very, very local scope instead of a broad global scope. And then a couple of different breezes that we have. Valley breeze, mountain breeze, and Adiabatic wind. Okay, let's jump into it. NASA gives us a picture of the Earth. You can see the picture of the Earth pretty good on the textbook photo and also on the iPad photo. What you don't see really too clear here is just that really thin slice of blue. Just to put it into perspective, that's the atmosphere that we're dealing with. All right, so on the grand scale of things, this is very, very, very small. When large weather patterns occur, they come in here. They might seem like it's moving fast to us, but at the big scale, this is just a very minute part of this entire globe. Okay, as promised, we took a look at the Earth and what occurs around that as far as the atmosphere. It's broken down into troposphere, which is the part that we live in. The tropopause, which is a small area, and jets, we're going to climb through that. As you climb through, typically you get a little bit of difference in temperature change. So climbing as we go up, it gets colder and colder and colder. And I can always see as I'm crossing through the tropopause, because momentarily that'll stop decreasing or maybe even get slightly warmer for a moment before it goes back the other way. Okay? And that's when you get into the stratosphere. We're not going to spend the scope of this class. We touched the stratosphere just as an idea. And that's it. There's really even the tropopause, there's not a whole lot of a discussion on that or the jet stream. We're talking about weather patterns that are going to affect the person flying that Cessna, that Duchess, that training airplane. Okay? The mesosphere and the thermosphere just as an idea where these guys exist. Okay. The atmosphere. Hold on for a second because we got to go through something important. And that is the atmospheric composition. Yesterday I mentioned to you guys that it's 21% oxygen. Okay? And I said that with a great deal of certainty because that's our percentage. Some 78% nitrogen, whatever, a little sliver there of argon and other gases and whatever in the world else exists out there. But that 21%, it exists all throughout the atmosphere. Look, it's sliced all the way through. 260,000 feet. Okay? So the percentage is not going to change. Later on, we're going to talk about how the human body reacts to a climb and different pressures. And we're going to discuss about hypoxia and how my body might have a lack of oxygen. Well, that has nothing to do with oxygen being removed from the atmosphere. It's the same exact percentage all along. What it has to do with my body being able to absorb the oxygen. Okay? And then something else was we were talking as we climb with this airplane, I get less air density. So I had less oxygen available up there, and my engine didn't perform as well. There was a lot fewer air molecules, so I had less drag. And we had one of those questions on the quiz. All these things have nothing to do with the percentage of oxygen. They're all functions of the pressure that exists. Okay? So just a key point and make sure that we're reinforcing something that we've already discussed, and that is aircraft performance and how it is affected as we climb, and also something we're going to discuss in the future. More on airplane performance, but then also we're going to discuss some of the physiological effects as we climb. Okay? All right. You can write down on your paper or your notes or jot it down in your brain. Heat is the cause of all of our weather. Okay? The transfer of heat is what's going to cause all of our weather. Depending on where I am, that transfer of heat is a lot different. Depending on what season I'm in, that transfer of heat is a lot different. Everything in the private pilot program is all focused on the northern hemisphere. So that part, that's fine. Without discussing seasons just yet and talking about only the Earth, and even better, talking about only the Earth absolutely still. So just hold on for a minute. We said theory. Let's have an Earth that's not rotating, okay? That's what we're going to do. I know it can't exist. We'd all fling off the side of this thing if it stopped rotating. But it's here and it's absolutely motionless. Near the equator, the same diameter energy from the sun, the same exact diameter here, the same exact diameter here, is absorbed by a smaller surface area. Because look what happens here as I go up on that polar projection. The same amount of energy is spread along a greater surface area of the Earth. So there's a little bit less heat that's transferred each square foot. If I just take a little block of land from here, there's less energy that's absorbed by that same block of land if I had it right here. Okay? This is what causes the global circulation patterns. Okay? And what they call this is convection. Convection is caused by that unequal heating of the Earth's surface. So the Earth's surface is heated, and then that heat is transferred to the atmosphere. There's very little of the sun's energy that's absorbed by the atmosphere as it comes through. The absorption occurs here. It heats up the Earth's surface, and then the Earth's surface heats up the surrounding air. Now, the surrounding air, as it's heated, it becomes lighter. I think we talked about that on day one, and I'm pretty sure I got north and south from everybody. This was an okay idea, right? So cold air is heavier, hot air is lighter. That hot air, when it's lighter, it goes up to roughly the tropopause, okay? Almost caps it off. And then it moves towards the poles, descends, and becomes cooler. Okay? Advection is the result of this air moving back to the equator. Now, this is a very, very simple model, but it forms the basis on everything else that we'll study with weather. Heated here, goes up, moves towards the pole. There's actually 3 cells, and we're going to see these in a moment. But moves towards the poles, cools, descends, and because it's a closed system, there's no escape of this out through the equator or anything else. It just follows along the surface and comes back to where it began. Okay? Okay, that's very, very, very theoretical. Now, hang on for a second. Let's still not move the Earth. The Earth is motionless. But that's a long ways for one air mass to move all the way from the equator to the pole. So what happens is it splits off into 3 cells. And this is still theory, yes. But this is very, very, very close to what actually occurs. Okay? We still don't have a moving Earth, though. And that's fun. All right? All right. So notice how I have a pressure system that's moving in this direction. Right? I got air that's moving up and over, descending and coming back towards the Earth. Okay? As it moves up, I have low pressure here. All right? As it's moving down, I have high pressure here. Now, we will talk about different layers and different flight levels and different ISO levels where the weather is studied and graphed and charted. Some of those levels are at 18,000 feet. And they'll take measurements of exactly what the high, low pressure system, which way the winds are going, what the temperatures are doing, and so forth. One of those analysis, one of those surface analysis occurs exactly there on the surface. And think about for a moment, if I have high pressure in my lungs and I blow it out of a straw like that, this is what causes that air to move. The high pressure from my lungs causes that air to move from my lungs out through the straw. Okay? So air will move from high pressure to low pressure. If I have a vacuum and I'm vacuuming the floor, that vacuum has low pressure. That's what causes all the debris and all the dirt and dust or whatever to enter the vacuum and go into the bag. So I know that air is going to move from high pressure to low pressure. All right, same thing here. I got low pressure on the surface, and I have high pressure on the surface here. So just planting a seed. We're really beginning to develop some thoughts here, and that's good. All right, some of these high pressures and low pressures are charted. And they're charted on a similar map like this. Now, this is a world map. It's very uncommon for us to see an entire world map of high pressures and low pressures. But what it allows for me to do, in other words, this is not a real chart that you would use. But it allows us to study it and for me to start talking about these ideas, and then we can gain a little bit of perspective and a little bit of understanding. That high pressure here at the surface, all of the air is moving quite rapidly towards that low pressure in the middle to the north. Right? And it will move exactly in that direction. Now, you gotta hang on for a minute. We still haven't started the Earth rotating just yet. That makes a big, big change. But this air coming from the high pressure is moving towards that low pressure. This air is moving towards that low pressure. Remember I said everything was going to be focused on that northern hemisphere, and that's exactly where we'll keep the scope of our discussion. Things act the same way in the southern hemisphere. It's just, it does an opposite direction. Okay? So we're only here. Now, these lines are very similar to contour lines. You remember yesterday we were looking at that sectional chart? And we had that thing out, and I told you that Florida was a terrible state because it was all flat. And we found the highest point on there, what was it, 305 feet? Ridiculous, right? Very flat area. So we don't see a lot of contour lines on that map. But if I were in Colorado, or I were in Georgia or North Carolina, I would probably see some lines of elevation. And those lines of elevation would describe exactly where changes in altitude occur, right? Changes in that ground level or that field elevation exists, okay? Those contour lines, if they're very far apart, it describes just a real shallow bank, right? I don't even see two contour lines on Florida map. They're so far apart, you won't even see them. But if I looked at somewhere where it had a whole lot of mountains, each contour line would be very close together. You guys have seen contour maps. You know what I'm talking about? Does anybody not know what I'm talking about? It's okay. Not everybody's a map guy, right? Or a map gal. But if you don't know what I mean with contour lines, let me know, because this is important for our discussion here. All right, so we're okay with contour lines. Contour lines describe areas of equal elevation. These are called isobars. Iso is, who knows, some language. Iso for same, and bars for millibar of pressure, or how much pressure do I have. These lines all describe equal pressure. Look at this. 1,008 millibars of pressure. 1,004, 1,000, 996. These are all described by those lines. When the isobars are spaced very, very far apart, that means it's a very shallow slope. This is your pressure gradient. And that pressure gradient is exactly what it sounds like, a grade. Either it's a very shallow grade moving upwards or downwards, or it's a very steep grade moving upwards or down. Just like on my contour map, if I had a very shallow banked elevation, on my terrain, or if I had a very steep banked mountain or a cliff, these lines describe exactly, in this case, how fast the winds are moving. Okay? So at a glance, I know 100% sure where the high pressure, where the low pressure is. I know what the exact pressures are following these lines around some of these areas. And I know exactly the relative speed of these winds. If it's fast or if it's slow. Here we have very, very little wind. Here I have a whole lot. Look at that. Very close together. Not much wind coming across Canada. All right? The earth still doesn't move. Okay. All right. Let's make this earth move. Okay? The problem with everybody when they start thinking about the earth not moving, and they start thinking now, okay, well, the earth moves. Big deal. I don't see the earth moving. I know you don't see the earth moving. And that's where humans, that's where all of us have a problem with Coriolis. Because Coriolis discovered something that was very, very unique and special. He discovered that, hey, if I have, in our case here, an object standing on a moving, rotating surface, then that changes the perspective of any straight line motion that this object observes. Our object here is a person. Who cares? Give him a name, whatever, call him Sam, whatever we're going to call him, right? But if I were standing opposite this gentleman and we were on the merry-go-round, and I take a ball and I throw it directly to him, it's not going to move directly to him. Instead, and you can see it just comes off to the side. And depending on which way that we're rotating, it goes off to that side. Okay? We are on a humongous merry-go-round. All right? So you saw this worldwide circulation. And even when we broke it up into something more realistic, there were only 3 cells. That is a large, large piece of property. Okay, so we are on a gigantic moving merry-go-round. What's special about this is that the winds are the ball. And the winds are 100% moving from high pressure to low pressure. It's being thrown exactly towards that low pressure. But it's not observed by us as going in that direction. We're on the merry-go-round. So Coriolis, above your friction level, above that 2,000 feet AGL, Coriolis effect is going to cause us to observe these winds 90 degrees to the right in the northern hemisphere. Southern hemisphere, it goes different because they're going the opposite direction. Their observation is 180 degrees different. Okay, so fantastic. What does that mean to me as an aviator? Why in the world are we studying this guy Coriolis and what he observed? Who cares? If I want to gain some perspective about these winds, I need to know which way are these things really moving. Okay, yes, they are really moving high to low. But remember, I'm on this thing and it is rotating at a very, very rapid pace. So what I see as I look up to the winds that are going to affect me in my flight are moving exactly 90 degrees to the right. 90 degrees clockwise. Okay? So anybody ever, it's fun because in this lesson, this chapter, and then in a couple other chapters, I get to give you guys some really cool tools to take to your flight instructors. They're going to love me. All right? Anyways, when someone says, hey, Coriolis effect, what is that? Because a flight instructor will come in and they'll expect you to stumble and stutter and not know what they're talking about. And then they get an opportunity to go get the coffee while you're trying to figure it out and look it up in the book. Well, Coriolis effect, guess what it is? It turns winds 90 degrees to the right. As soon as you say that, boom. Okay? They want to press on it just a little bit. Well, why does that happen? Well, it's similar to us being on a merry-go-round and the ball being thrown at us goes to the right. It's the right answer every single time. There's Coriolis effect, okay? All right, nothing magical about Coriolis. Oh, by the way, just real quick, we will go into this a little bit later too. But if these winds are moving 90 degrees or clockwise to the right, okay, take a look at what kind of surface I'm going to get going around, what kind of winds I get going around this low pressure. They move counterclockwise. You guys see that? Just like a hurricane. A hurricane is just a large, low pressure. And all the winds move around that counterclockwise, right? I know that because we see hurricanes all the time. And then we prepare for them. Everybody buys their food and water, and then it hits somewhere else, right? But counterclockwise around the low pressure. Around a high pressure system, it goes clockwise. So I know automatically just by looking at this chart where my high pressure system is, where my low pressure system is. I can begin to gather some more information. We'll talk about how I can estimate or think about and expect certain characteristics just because it's high pressure or low pressure. I also know what the pressure values are across my region. Okay, fine, fair enough. But more importantly, I know the wind direction parallel to the isobars, moving counterclockwise around a low and clockwise around a high, and I know the approximate speed or the relative speed of these winds. So just by looking at a chart like this, I can get a lot of good information, okay? All right, now, same type of thing with Coriolis effect. If you take a tangential path or something that's just a straight line from a curved line, such as one of these flight paths going around the United States or that part of our globe, you'll see that the actual flight path is like this, whereas your destination may be over here. It was interesting to me flying over to Moscow from Miami. Well, number one, we had to fly up the eastern seaboard and then up and over and come through Europe. But it was interesting when we were getting to a point where the line looked like it was almost straight and the heading continued to change, because they had the little thing on the screen. That was fun. But anyways, just the great circle and how we move around and plan for a destination in a long ways off into another continent, right? You won't actually have that same exact heading the entire flight. All right, here we go into Coriolis effect and talking about near the surface. I told you guys that below 2,000 feet, we have friction level. The winds are going to decrease in velocity just a little bit. And as we move higher and higher, they typically move much, much faster. But below 2,000 feet AGL, and there's not a sign up there that says 2,000, this is friction level. I get it. But approximately 2,000 feet AGL and below, the wind speed starts decreasing a lot. So Coriolis effect is reduced. I no longer observe winds exactly 90 degrees to the actual motion of that wind. Instead, I observe them at a slight angle pointing towards the low pressure. Because winds move from high to low pressure anyways. So if I get a little bit less Coriolis effect, well, they're going to move a little more towards that low pressure, but at an angle, okay? And that's just what we observe here on the upper level wind flow. You got Coriolis effect causing that thing. Still, I have clockwise motion around the high and counterclockwise pressure around the low, but just a little bit less of that, and it goes towards the low pressure as you get into the friction level. Okay? A pilot, a long time, in fact, the first pilot that I ever took flight lessons with, he told me a long time ago, if I stand with the wind at my back on the surface, then I can point my hand just like this, and I know that's where the upper level winds are. And it's very effective. Is it true 100% of the time? Well, absolutely not. But on the surface, I don't have as much Coriolis effect. So all I do is just take and add another couple degrees, and I can look up, and usually that's the direction that the clouds are moving. Okay? Just a quick estimation. If I'm flying my airplane and I know I'm above the friction level, I know the surface winds are just a little bit counterclockwise. So if I'm making runway selections and I'm coming up to where it looks like this might be one runway or another, I got to crosswind regardless. This will help me gather information for these airports that don't have weather information. I can start forming an opinion 30, 40, 50, 60 miles away, because this is the time to start planning for that descent and start planning for how am I going to join the traffic pattern. I don't want to show up to the runway and start making that decision then. Pilots do it all the time, but it's not a great idea. Start getting that information and start doing the best that you can to collect it early, okay? Okay.
How big is this difference, like 30 degrees or 40 approximately?
All depends. Yeah, you know, the gentleman that told me to do that, at the time, I was born in Florida, but I went to high school in Michigan. So I got a little bit of cold weather on me. Wow, today was cold though, for me regardless. Anyhow, so the gentleman that told me that was in Michigan, and he told me just take about 30 degrees. Don't go your full 45, go about 30 degrees, and this will give me an estimation. Let me tell you guys something. I work around a lot of younger pilots. Younger, not just younger like they're 15, 16, 17, or 20 or whatever. But I work around a lot of younger pilots sometimes that just haven't been flying a whole lot. And I'll do something like that. I'm at the surface and I got the wind at my back. We're in a non-towered field. And I'll tell them that's where my winds aloft are. And I'll take a look and check them sometimes. They'll go in and look it up. And they'll go, does the old man know what the hell he's talking about? And they look at me like I actually discovered fire right then. How did you do that? So yeah, some of the old school tricks are kind of cool. Okay, now some of these, remember we had those 3 cells. So those 3 cells will describe some of the 3 cell circulation patterns, semi-permanent areas of high pressure and low pressure. Now it says semi-permanent. I do love this about weather theory, and that is nothing that we say is going to be permanent. I can't tell you this will always happen. I just shared a nice story with you guys about, hey, this, move your arm this way and take a look, right? It's not always going to work, but a lot of times it will. Same thing here. You get prevailing westerlies, northeast trade winds, polar easterlies. These are wind patterns that we can expect on a daily basis. And we can also expect when these do not exist, if the winds are moving contrary to the normal, guess what? Something caused that. What is that something, and what else is it likely to produce? That's all I've been trying to do whenever I teach the weather classes. Give people just enough information where you guys can go out there and begin to make these estimations yourself. Kind of formulate an idea of what's going on in the weather before I get to that weather forecaster, before I talk to them on the phone. Because I can tell you my first and I had some pretty good instructors, but my first couple of times talking to a weather forecaster, I had to call them on the phone. There absolutely was no internet when I first started flying. Okay? When I called him on the phone, that person may as well have been speaking Greek to me. I had no clue what they got done telling me. And the flight instructor came over and said, okay, you get your weather brief, we good? Yeah, I think he already knew. Yeah, of course we're good. But he also knew I had no clue what I just listened to. I was on that phone for 20 minutes and I had no more information at the end than I did at the beginning. Okay? So what I'm trying to do is just give you enough of this information. So start forming that opinion now. Start reading the weather reports now. Start using some of the knowledge that I'm going to give you now and start getting an idea. Hey, this is what I think is going on. Then pop on the local news. Oh yeah, look at that. That is actually, they're saying some of the stuff I heard in that class. Okay? So use this stuff right now to help out a whole lot. Okay. These are worldwide or global circulation patterns. The local circulation patterns exist and they can make a change as well. And they can make a change contrary to anything else that we've had. So I could have the easterly trade winds that are coming through a certain area all the time, and I understand that, and that actually happens. But where I live is next to the beach, and I get this, okay? So you just be prepared for that. Take a look. This is the sun's out, right? Sun's out, guns out. I got warm weather here. It's heating up this surface. What happens with the surrounding air? Heats up, gets lighter, correct? What's that called? Convection, okay? And I could remember yesterday when I was talking, just for a second, I know I get sidetracked. I got like ADD or something, I don't know what it is. But anyways, remember yesterday I was telling you guys that there was an airplane and we were talking stability. We said it got bumped up because of that road. And I said that if you stand on a road and it's really hot, you stand on the grass, it's not so hot. This is the same type of thing what's happening here. If it's a road that happens, we'll call them thermals, right? You just got a thermal, and I got a nice slide of that. But anyways, you guys are absolutely correct. It heats up the ground. That ground now heats up the air. The air warms. It gets warm. It gets lighter. It moves up. And the return flow comes over to the cool air and makes a nice breeze off the ocean all day long, okay? Guess where Fort Lauderdale Executive is? My group is going to Fort Lauderdale. Woo, woo, all right. Guess what you're going to take off on almost every single day? I did say almost, and it's runway 9. Because runway 9 faces straight towards the beach. Right next to the beach, man. Okay? So that's the way you'll take off almost every single day. Here I say again, almost. You just can't get a straight answer out of me at all, right? Some days you'll take off on runway 27. So study that chart and you know how to taxi out to runway 27, or else you're going to sit there looking like a dodo when they tell you how to taxi out there, okay? All right, so that's my sea breeze. Take a look here. Land breeze. With a grain of salt, because it depends on where you are. And I can tell you that where we are, normally it won't change day or night, but this is a phenomenon that can occur and is common, very, very common. So nighttime comes. The biggest thing is here, not that this occurs all the time, but let's start thinking through this. What happens to this surface? What happens to this surface once the sun goes down? Okay. Hold on with me for a second, because we're going to talk about why it cools down. Okay? Why does that Earth's surface cool down when the sun goes away? It's not absorbing heat anymore. I understand that, right? So if it's not absorbing heat, what's happening? Radiation. Yes, that's the correct word. The heat radiates off the Earth's surface right there. Now, tell me if I'm wrong, but is that a radiator back there? Maybe? That's not a radiator? Or is it? Okay. The reason I had to make sure is you won't find one of those anywhere in Florida. Okay, so I was really hoping that's what that was. All right. Yeah, that's exactly it. It's radiating heat. I say radiation fog, or talk about radiating heat in South Florida, and I got people all of a sudden, they think that we got a nuclear explosion going on. There's a radiation. No, it's radiating heat off the Earth's surface, right? So this loses heat, that cools, and that now cools the surrounding air. How much does cold air or cool air weigh compared to warm air? It weighs more. So now this goes back towards the surface, advection, right? Brings it, high goes to low, ta-da. Okay, so we've already gone a long ways with weather. I know, because I look out there and I see some smiles and I see eyes that are open. I know the classes when I got half the class lost, because by this time they're going, right? And they don't have a clue what I'm talking about. You guys are all paying attention. This is great. You right now, right at this moment, know more about weather than a lot of student and private pilots, okay? So don't forget it. Just practice it, okay? All right, here we go. Now, there was a fancy word on there, and adiabatic expansion or adiabatic flow. Honestly, I can't even remember. That should give you an indication of how important this is. Not one bit at all. But as air flows upstream, it does cool slightly because of expansion, all right? And kadiabatic expansion does occur. So air will cool slightly as it moves up. Now, it doesn't have to be a terrain feature. This is a terrain feature. This is Mount Everest or whatever in the world that is, okay? And as air is moving up that, it's cooling. The same thing will occur if air moves up because of any other phenomena. So because of a front coming through that's causing it to move up, because of convection, because of any other reason in the world, as it rises, it will expand and cool, okay? And it'll do that at a certain rate. If I'm not mistaken, I think it's 3 degrees Celsius per 1,000. But again, if I'm, kind of guessing on some of this stuff, well, you maybe take it for a grain of salt. We're not going to solve all of weather's problems today. What we are going to do is become really good aviators and know how to forecast and make some good decisions on when to go and no go. Same thing going down. Exact same thing going down. As air moves down, it will typically warm. Right? It'll condense and it'll also warm. As it moves down, not as I move through it. We're going to talk standard lapse rate again and adiabatic, dry and moist lapse rate. Okay, we will. But again, all right. Here I got this. Minus 20, high pressure. There's a cold downslope wind. Gets down to the low pressure and it's much warmer. Now, do I expect this automatically? The answer should be kind of yes. And here I'll tell you why. Because if I'm in an airplane and I begin to climb, what happens inside that airplane with the wind, with the air? What happens inside that airplane? Temperature does what? It decreases quite a bit, doesn't it? It's going to decrease a lot, okay? Decrease 2 degrees Celsius per 1,000 feet. I'll tell you, it's not uncommon for student pilots, and I don't know why. It's not uncommon for student pilots to start everything that they do, and they seem very well organized and planned, and they work the radios well. So far, I'm just in heaven. This pilot I love everything you're doing. ATC can work with you. We're getting good handling. And they climb off the runway and they make their turn to the northwest practice area. And then they ask, and they just spoil it. They say, well, what altitude are we going to? You're a pilot. What altitude do you want to go to? What did they tell us back there? They said maintain VFR, clear for takeoff. Don't go in a cloud. How about you climb to 71 degrees Fahrenheit so it's cooler in here, because right now it's 90, right? So anyways, yeah, it does get a lot cooler as we climb. That's kind of nice. So I do expect this to happen, and that phenomenon occurs. All right, unless maybe I have a very, very strong wind and then a warm downslope wind coming across. Again, I got 10 degrees Celsius, but a very strong wind comes down 20 degrees Celsius at the bottom.